What we're going to do, does everybody see how there's like these two-dimensional shapes here? So this right here is an axis of rotation. We take that two-dimensional shape, which is a triangle, and we rotate it around that axis of rotation. You can kind of see as we rotate it around in this second picture, it just kind of goes on to the other side. We can't really see it too well because obviously we're trying to represent three-dimensional things in a two-dimensional piece of paper. So you got to use a little bit of imagination here. But as we rotate it, hopefully you see it turns into a three-dimensional piece, a three-dimensional solid. So a two-dimensional triangle, when we rotate it, became a cone. Similarly here, we take this two-dimensional circle. Hopefully you can see there's kind of a little bit of a gap. There's a little bit of air in between there and the axis of rotation. So as we rotate that circle around, we're going to get like a little donut hole in the middle of our shape. Same thing down here. We kind of have a triangle here. It's cut out this way. Let's see if I can color this in. So this is all hollow here. So as we rotate that around, we get all this hollow space in the center. Essentially, all we are doing is we're going to take two-dimensional shapes and we're going to rotate them around an axis of rotation in order to get a three-dimensional shape. And we do this all the time in calculus, actually. You will talk about that when you get there in 2 to 3 years, maybe for some of you. So I think this is a super fun lesson. We're going to start out real simple first. Before we even try to find volumes of three-dimensional solids, we're going to find areas of just two-dimensional figures first. The process that we're going to use to start all of these is going to be kind of the same. We are going to start by restricting the area in which our graph appears. So we are given two things to start these problems. We are given the equation of the line, and we're given some boundaries. Now, these boundaries, they might be restricting the x's or they might be restricting the y's. In this first problem, we have restrictions on the x's. And then our goal is to find something called the area under the curve. So we will talk about that when we get there. So let's first talk about where is our restriction. So it's on the x-axis, which is here, and it's between the 2 points 0 and 3. So I know that I only want my graph to show up between 0 and 3. The way that we're going to graph our lines is maybe a little bit different than how you would expect we graph our lines. We know that lines take the form y equals mx plus b. So if I look at that line right there, I have a slope, and I would know that my y-intercept is 0. However, instead of doing that for every single one of them, we are literally going to simplify it down to finding the two endpoints of this line. So I want to find 2 points here. I want the x values of my points to come from my restrictions. So I want the two x values to be 0 and 3. This is how we're going to start all of these problems. Now, to find the y values, all we're going to do is take my equation and plug those numbers in for x. So y equals 2 times 0, or y equals 0. My first point is then 0, 0. And then y equals 2 times 3. So y equals 6. My point is 3, 6. So when I put these into my graph, I have 0, 0, and then let's get a point 6 over there. So we have 3, 6. And then if I connect those 2 points up, right there, there's my line, y equals 2x. That's all we're going to do for graphing the lines for these problems. Does that make sense how I got those? Okay. Now, we need to find the area under the curve. So I need to define what is the area under the curve. Well, the curve in this case, or in all of the cases that we're going to see, our curves are going to be straight lines. So what is the area underneath this curve? Here's all the area underneath it. Remember, we're stopping at 3, so it shouldn't go any further than 3. And then we kind of have to use our imaginations a little bit. What shape did I just create? What two-dimensional shape is that? The triangle, right? So to find the area under this curve, for our purposes, not calculus reasons, we are going to just literally find the area of that triangle, which is 1/2 base times height. The base of my triangle right here is the distance from 0 to 3, so that's 3. The height of my triangle right here is from 0 to 6, so that's 6. The base is 3. The height is 6. The area of this triangle is 9 units squared. Does that make sense? Area under the curve. Okay, so let's start the next one. We are going to start, I always like to start by putting my restrictions into my graph so I can kind of visualize them first. I see 2 is less than y is less than 6. That means my graph is only going to show up where the y values this time, so the vertical axis, are between 2 and 6. So let's put 6 up here. Let's put 2 maybe right here. I'm going to graph this line the same exact way that I graphed the last one, not by trying to figure out rise over run, all that stuff, but literally just by putting in some endpoints. So I'm going to have 2 endpoints. I know what I want their y values to be, 2 and 6. This is a little bit different because we're not just plugging in an x anymore, we're plugging in for y. So I have to go and plug in 2 in the y position in my formula and 6 in the y position in my formula. Okay, got those? Oops. Got those? Now we're just going to solve for x so that we can figure out what those x values are going to be. So minus 4. This is -2 equals -2/3 x. If we divide by -2/3, that's the same as multiplying by -3/2. So we could rewrite that as a +3 is our x. That makes our first point 3, 2. And for our second point, again, we're going to have to divide by that -2/3, which is going to get us a -3 as our x. So we want -3, 6 as our second point. All right, you with me? Now we're going to graph those 2 points. I need a point at -3, 6. So that's going to be all the way up here. And then I want a point at +3, 2, which is down here. And connect them. Everybody got our line? Nothing too crazy? Now again, let's refer back to those directions. It says we want to find the area under the curve. So I'm going to take that line that I just drew and I'm going to find all of this area underneath it. So anything that falls underneath that curve is what I'm finding the area of. Do we know what kind of shape that is? Anybody? Anybody? Caitlin? Yeah, this is a trapezoid. So the area of our trapezoid formula, area equals 1/2 height times base 1 plus base 2. Let's define our heights and our bases. Remember, the bases have to be parallel to one another. So the 2 lines that are parallel are these 2 vertical lines. So our 2 bases, we're literally just going to count. So from 0 to 2, that's 2. From 0 to 6, that's 6. And the height is what connects the 2 bases together. So the distance from -3 to 3, that height should be 6. The area then of this shape, 1/2 times 6 plus 2. 8 times 6 is 48. Half of 48, 24 units squared. Everybody okay with this? When it says find the area under the curve, that's all it's asking you to do is to figure out where your line is and then find the area of that shape underneath it. Good? Okay. Now we're going to make things a little bit more complicated. So turn it over. Now we are finding volumes. So we're going to find three-dimensional shapes. We're going to start pretty much the exact same way. I have restrictions and I have a line. Let's start by putting my restrictions on my graph because I like to do that first. I'm restricting the x's as I can see here because that's an x value. So between -4 and +2, that's where my restrictions are going to be. Okay. Now I need to graph the line y = 3. So I want two endpoints. Hopefully these two endpoints are a little bit easier to get, actually. Oops, that's awful. I know that my x values are -4 and 2. My y values, y = 3. What kind of line is y = 3? Anybody know? Y = 3 is a horizontal line. So no matter what my x value is, my y value is just going to be 3. So I have 2 points. -4, 3. Let's call this up here 3. So that's my first point, -4, 3. And my second point, 2, 3, is right here. Let's connect them up. So far, so good. Everybody's got that? Okay, here's the new thing. We're not finding the area under this curve anymore. We are now going to take that line and revolve it around the x-axis. You're going to have to use a little bit of imagination because I can't, move my arm and show you what this looks like. But you're going to take this line and imagine we're rotating it around this center line here. That means that line in black up at the top is going to go all the way around that purple line, okay, until it's the same distance on the other side, and then all the way back up. I'm going to try to represent this on this paper, but keep in mind, I'm drawing on a flat surface, so it's not going to look super perfect. But that basically means I'm going to take every point, I'm going to rotate it around all the way, and then come back. I'm going to take this point, rotate it all the way around, and then come back. When it gets to about halfway, so it's exactly on the other side, it should still look kind of like that. Okay, use a little bit of imagination. Imagine it's three-dimensional, not two-dimensional. What shape did I just create by rotating that all the way around 360 degrees? Yeah, it's a cylinder. So when I rotated this, I created a cylinder. So now I'm going to find the volume of a cylinder. To find the volume of a cylinder, I'm using the formula pi r squared times height, which means I need to identify the radius and I need to identify the height of this cylinder. Your center of rotation, so that x-axis in this case, that's going to be the center of your shape. So to find the radius, the distance from the center to the outside, I'm just going to count up those spots. It goes from the 0 all the way up to the 3. So this distance is 3. The height of my cylinder will go from base to base. So what is this distance here from base to base? Well, it goes from -4 to 2. So that distance is going to be 6 for my height. Does that make sense how I'm getting those numbers? Then we put it all together. The volume equals pi. Radius is 3 squared times 6. And I believe this is 54 pi. Oh, gosh. Which, if we round that, is 169.6 units cubed. Does that make sense? Hopefully, maybe, yes, maybe a little bit. Okay. Let's do another one. Starting with my restrictions, this time, look at that. I'm restricting the y's, so I'm going to look at the y-axis this time. I want those restrictions between 7 and -2. Let's put those on there. This time, my line is x equals -2. X equals hoi vux. That's a vertical line through -2. So our 2 points, if we think about having 2 endpoints, If we have our y values, our 2 points are just going to be -2, -2, and -2, 7. So let's graph that. Let's say this is -2, -2, right down here, and this is -2, 7. Okay, everybody got our line? Now, I'm going to rotate this. We need to be careful because we're not always going to rotate around an axis. This time it's telling me to rotate about the line x equals 1, which x equals 1 is the line, let's say this is 1. X equals 1 is this line right here. So I need to rotate that line that I just graphed around that line x equals 1. So I'm going to start my rotation. It's going to go vertically this time. You're going to have to trust me. It's going to go, okay, that's about a quarter of the way. That's about halfway. And then all the way back around. Okay, about a quarter of the way. That's about halfway. And then all the way back around to the start. Hopefully we see another cylinder. So let's calculate volume of that cylinder. In order to calculate the volume, I need radius and I need height. That center, the thing that I rotated it around, that is representing the center of my shape. So the radius is this whole distance. The distance from -2 to +1, that distance, my radius, is going to have to be 3. Yes? Everybody understands that? Okay. Then the height, the distance from top to bottom, base to base, from this was at -2, this was at 7, that distance is 9. Volume is is pi radius squared times height. I believe this is 81 pi, or 254.5 units cubed. Any questions on that one? Okay, we're going to switch it up. They're not always nice horizontal and vertical lines. So now we're going to get into graphing what it looks like when I have diagonal lines like y equals 2x or y equals 3x minus 3. Our process should be the exact same as we've been doing. I'm going to start with putting my restrictions on my graph. So between where x is 0 and where x is 4. Let's call that 0. Let's call this 4. To get my 2 endpoints, I want where x is 0 and where x is 4. So I'm going to plug into my equation to get those y values. Y equals 2 times 0. And y equals 2 times 4. So my 2 points are at 0, 0. And at 4, let's call this 8. Everybody good? Everybody got my line on here? Now, how am I going to rotate this? I'm going to rotate this around the x-axis. So it's going to rotate around this line in purple here. That point 0, 0 that is already sitting on top of that line, that's not going to move. That's going to stay there. Everything else is going to rotate around it. So let's start with this point up here. This is going to rotate. There's about a quarter of the way, there's about halfway, and then it comes all the way back up. What does that look like? Well, that just means that this is flipped all the way down here. What shape is that? It's a cone. The volume of a cone formula, 1/3 area of the base, pi r squared, times the height of that cone. Same process to finish this off. We're going to figure out what's the radius of this cone. So the distance from center out to the edge, if we count those spaces up, that should be an 8 for our radius. And then the height of our cone, the distance from the top to the bottom, that's 4. Volume equals 1/3 pi. Radius is 8 squared times the height is 4. Let's see, 64 times 4, 256 divided by 3 doesn't come out to a nice number. So let's do 256 times pi divided by 3, which gets me 268.1 units cubed. Any questions so far? We're going to do one more and then I promise we will move on. Okie dokie. So, same deal. We got to start with my restriction. So I'm restricting the y-axis this time. So between 6 and -3, let's do like this. I'm going to find my endpoints of this line. I know that my endpoints are going to have y values of -3 and 6. And I need to figure out what those other x values are. So we're going to plug in -3 into my equation and solve. So this is 0 equals x. And then same thing over here. 6 equals 3x minus 3 plus 3 on both sides. Divide by 3. So x equals 3. So my 2 points. 0, -3. Right here. And then 3, 6. Let's put +3 over here. 3, 6 ends up about there. Okay, pay attention to where we're rotating. We're revolving around the y-axis. So I'm going to revolve around this guy right here, which means it's going to go whoop, all the way around. Reflected it that way. We've got another cone. So we want the volume of this cone, 1/3 pi. Radius squared. What's the radius of this cone? From the center to the edge, that radius is 3. It's 3. And then the height of that cone, from top to bottom, the distance between 6 and -3 is 9. So this is 81 pi divided by 3, so 27 pi. Or as a decimal, we'll go 84.8. Any questions on that?